So today I need to do an experiment, and I decided to take you all with me. What I have here is something I've shown in multiple videos already. It's a scintillating crystal, which we can use to measure radiation. And then what I have here are about 10 of those crystals stacked on top of each other and glued together with a special optical glue so that the light can travel through easily. And if you look into it, it looks a little trippy because it looks a lot shallower than it actually is. And then you can see the connections in there from where all the crystals are glued together. So what I want to know is what happens when we take these and glue them all together, and does the performance get better, worse, or is it not affected at all? What I'm going to do here is I'm going to run two experiments, one as a control where I use the single crystal, which I know should work, with a PMT that I know should work. All I'm going to do is put a radioactive source near the detector, measure the radiation from it, and look at the radiation in an oscilloscope. And if these words are confusing you, go back and watch some of my old videos where I explain what all this stuff means. And when I go back and look at this data, I should see a certain width and height of the pulse. And then by comparing those two between the different setups, the single crystal and the glued crystal, then I can get an idea of the actual performance of the crystals in these different arrangements. So let's glove up. By the way, this is a good time to mention, I'm not a chemist, I'm a physicist, so some people may be upset by the way that I use gloves and cleaning things in my lab practice. To that I say, we are careful when we need to be and we're not careful when we don't need to be. This is mostly to protect my own hands and keep the crystal relatively clean, but things don't need to be completely sterile here. It's not an operating room. Let's clean the crystal. So like I said, it's not perfectly sterile, but if it's clean enough to pretty much see through, then you should be good. And this is the photomultiplier tube and base electronics that I'm going to be using for this test. And as you can see, it still has some optical coupling grease on the end. It's pretty messy, and this has been tested and works. So I'm going to clean this. Once again, not perfect, but pretty clean. Now the goal is to optically join these two surfaces. So we need to use optical coupling grease. This grease matches the indices of refraction of the two surfaces so that when the light reaches the boundary between the crystal and the PMT, it can go right on through without getting reflected or refracted a different way. Now we have some grease, so we squish these together. So now you can see there's a few air pockets in there that we're trying to work out, but for the most part, it has been optically coupled. Now the issue is that these detectors turn the radiation into light and then measure that light. But if we have all kinds of light in the room coming from the ceiling and everywhere else, how do we get rid of all that light and noise? The answer is we use one of these babies. This is a dark box, and we can open it up, and inside here we can stick our detector that we are testing, connect the cables on this side, which come out this side, and then we can close it back up, lock it up, and then do our experiment in here. So I have our coupled assembly here, which I'm going to carefully place inside the dark box. And as you can see, I have connected the proper cables. Red is for high voltage, and green is for the data coming out of the detector. So let's close it up. And if we set this to the proper voltage polarity, power up, we already see some pulses coming in even though we don't have a radioactive source. And that's because on Earth, we always have cosmic ray radiation showering down on us at all times. Nothing to worry about. Now, if I add a radioactive source near the detector, we should see much faster counts, which we sort of do. So now what I want to do is take just one of these mini pulses that we're getting, freeze it in time, and then zoom into it and take away the information that I want to get from it. You can do that like this. So after doing that, you can see that this pulse is roughly 1, 2, 3, 4, 5, 6, 7 maybe blocks long before it returns back to its 0 point, and roughly 1, 2, 3, 4, 5 blocks high. And if we read here, this is 200 millivolts per division and 10 microseconds per division. So if we do the math of how many blocks wide and how many blocks tall this pulse is, we can figure out the voltage, which represents the energy of this pulse, and we can figure out the time that it took this pulse to go up and then come back down. So now I can repeat the entire experiment for the other detector, and we'll see if there's any difference.